So good morning to everyone. I'm Carsten Schmidt from DSpace, as already mentioned, and I was invited to talk a little bit about virtual validation. I think this is a topic that is not so much used like, for example, hardware-in-the-loop simulation, but it is a future topic and it will be used more and more in the future, I think. I will give you the outline of this presentation in a moment, but to make you a little bit curious about virtual validation and to give you a little bit motivation why you should not fall asleep in the next 2 or 3 hours, I would like to show you a little presentation at the beginning. And so think about you have just developed an adaptive cruise control algorithm and you want to test it. And of course you could get an ECU somewhere and a car where you test it, and then you can load it on the ECU and then you can drive the car, of course. But yeah, you have to have all this hardware, of course. And of course it's a little bit dangerous because if the algorithm doesn't work, then you can produce a crash or something. And so an alternative is to use virtual validation, and then you can do the following. So you can start a virtual test bench and do a virtual test drive. And I can just start a predefined maneuver. You could have defined it previously. And you have plugged in your algorithm to this simulation tools here. And now you see this car has this adaptive cruise controls built in. And let's see what happens if some traffic comes. And here at this point, the adaptive cruise control is powered on, and you see the speed is 120 kilometers per hour. And now you see here is another car in the way. And so the adaptive cruise control just slows down the car. And basically, it follows this car at a certain distance. And now the sensor here detects that the car is not anymore in front of you, and then the speed is again increased. So this is one example what you can do with virtual validation, and hopefully during my talk you will learn how the techniques behind this work. Of course, this looks a little bit like a video game, but it's not, because the algorithms behind them are really algorithms that could run in the car, and you have a kind of sensor evaluation, and based on this distance measurement and so on. So this is very realistic what's behind the scene, and you will learn how that works and what tools play together to achieve this simulation here. So let's have a look at the agenda now. So first of all, I would like to introduce DSpace a little bit, because I think it can be quite interesting for you to know a little bit more about DSpace. Because if you really will work in the automotive area, then it's pretty probable that you find at least one DSpace product wherever you work. Because DSpace has quite a lot of products, and almost any company that has something to do with automotive has at least one DSpace product. And in this course, I will also introduce a little bit of myself. So I will explain a little bit what I do at DSpace. Maybe it's interesting for you too. And in the main part, so that's this part, I will tell the theory of virtual validation, of course, related to the DSpace tools, but basically quite general. And of course, I will present the benefits of virtual validation too, and I also will present some practical use cases. So how real companies, how real customers use virtual validation. And the last part of this presentation is a tool demonstration. And basically, we will go step by step through all the tools that make it possible that this simulation that you have seen runs. Okay, so let's start with the first topic, the introduction of DSpace. DSpace is actually quite young. It was founded as a spin-off from the University of Paderborn, and it started in 1988 with 4 engineers who had an idea. The idea was to provide tools to make the development of electronic control units faster and easier. And so I think it's quite astonishing. Also, we had this 25th anniversary at DSpace some years ago. So, for example, compared to me, DSpace is quite young, and but it grew to a really big company, a really grown-up company, and that's how DSpace and his one of the founders look today. So DSpace, as I said, has become a grown-up company. This founder, our CEO, Herbert Hanselmann, was elected to the Entrepreneur of the Year. He has several social activities. He is member of the University Council of Paderborn and so on. So it's quite impressive what he's done in these 25 years. So this is the headquarters in Paderborn, and currently in this headquarters there are about 900 employees. And in addition to that, there are additional offices in near Munich, Stuttgart, and Wolfsburg, where there are additionally 100 employees. And yes, these offices here are called project centers in the sense that only customer-related things are done there. Engineering for the big automotive companies in these areas, and all the development is done in the headquarters in Paderborn. And DSpace also has employees in other countries. There are, for example, offices in the USA, in the United Kingdom, in France, in China, and in Japan. So DSpace has become quite international, and all these offices here are mainly or play mainly the role like these project centers that I've mentioned before. So they are mostly doing things that are directly related to customers, so there's no product development there, but there's engineering and sales, of course. And in all these foreign countries, there are, in addition, 230 DSpace employees. So the total sum is 1,240 employees of DSpace. And if you think it's just 25 years from the founding, it's quite nice, I think. Okay, so let's go a little bit into what DSpace does. So DSpace, so here's a statement. DSpace develops tools, hardware and software, that allow development of control systems and electronic control units. I think it's quite clear to you what it means. It's a little bit difficult sometimes to explain it to persons who have not an engineering background. Okay, and DSpace is actually an acronym and stands for Digital Signal Processing and Control Engineering. So what customers do we have? So actually 80% of our customers are from the automotive industry, and the 20% of the customers are, of course, from other areas, which also have the task to develop control units or something. So the most important other customers are from aerospace, medical technique, agricultural machines, and so on. So that are our customers, and because we have 80% of our customers from the automotive industry, DSpace tries to do a lot in this direction. For example, to support techniques that are typically used there, for example, AUTOSAR or all kinds of standards that are used basically there. Okay, so let's go a little bit into the products. I think it could be interesting for you to have an overview about the products of DSpace before we really go into the topic of virtual validation. And for that purpose, I have this image of a V-cycle here. I think you discussed this development model, the V-cycle, in this lecture here. And so you know, basically, you go from requirements to software architecture down to the actual coding on the left-hand side of the V-cycle, and then you go up from unit tests, and you test the integration up, and at some point you test the whole system. That's what the V-cycle tells you. And I would like to use a quite adapted form of this V-cycle to present the most important DSpace products to you, because they can be quite nicely arranged here, and you can associate the most DSpace products with certain places in the V-cycle model. So let's go through the most important products here. Of course, DSpace has a lot of more products, but I will pick the products that are most important and that has something to do with this virtual validation. So let's start with the top left corner, software architecture. So what tool is provided by DSpace to support working with software architecture? So the tool is called System Desk, and System Desk is mainly an AUTOSAR architecture tool, but it's a little bit more than that, and compared to other AUTOSAR architecture tools. But so you see, you can, for example, create an architecture consisting of several software components and connections and so on. But you can also do certain things related to base software configuration and so on. And actually, this tool plays a quite important role in the virtual validation process. So we will come back to it later. So the next interesting tool is rapid prototyping. I think you may have seen this also. So this is basically the first thing that was invented by DSpace. So you can just create your control algorithm in Simulink and load it to a micro AutoBox, for example. And this rapid prototyping units has certain I/O features, and then you can directly plug it into your car and do a prototypical test your idea of a control algorithm and see whether it works. And if it works, then you can create a real ECU for it and make a serious production code or something. Okay. The next thing is how to develop actual code that can be used on real ECUs. So of course, related to the rapid prototyping code, you have to meet efficiency goals. You may have to do all the computations in fixed time for better efficiency and so on. And the tool to be used for that is TargetLink. The TargetLink is a generator for production quality code. And the code is generated from Simulink or enhanced Simulink models, which are called TargetLink models. And so this is comparable to the embedded coder of MathWorks, if you like. But it's also interesting to have a little bit deeper look into that, because it has, for example, some AUTOSAR features, and AUTOSAR is also quite important in the area of virtual validation. Okay, the next part is the testing part, and so I think the testing can be explained by starting with hill testing. So you also heard about hill testing in this lecture. DSpace develops a lot of different hill simulators. All of them are built according to customer specifications. And of course, you need some additional tools to be able to use such hill simulator to really test ECUs. And so you need a kind of interface tool to, for example, to define tests, to visualize tests, and so on. And these interface tools, these are shown here. So first of all, we have a tool that is called Control Desk. And Control Desk is a kind of graphical front end for measurement and simulation in this hill simulation. So basically, you can read data of the ECU and stimulate data of the ECU. And you can also define quite nice control instruments that really look like your cockpit in the real car. And actually, you have seen this in this presentation in the beginning. The cockpit was basically modeled with Control Desk. And of course, we come back to this tool in the context of virtual validation too. Okay, then we have Motion Desk. And Motion Desk is a tool, the DSpace tool, for 3D validation of cars and environments. And of course, you have also seen this tool in the starter presentation too. So this is of course very important if some simulation is related to movement of cars and so on, and checking the environment for certain things. Yeah, that is a tool to be used there. And then there's a quite important thing. These are the automotive simulation models and the tool which allows the high-level configuration of that. And that is because if you do hardware-in-the-loop testing, you somewhere need an environment model that pretty much reflects the reality, so that you can you can simulate it in a sufficient realistic way. And that's why DSpace provides Simulink models for all kind of the environment. So, for example, you can simulate engines, you can simulate the powertrain, you can simulate vehicle dynamics, you can simulate traffic, and so on. And basically, these automotive simulation models are just normal Simulink models, which are open to you. So you can have a look into it, see how it is modeled. You can even adapt the model if you maybe have a little bit different requirements and so on. And that's a very important product to make this HRL testing really suitable. And there's another level of configuration that you can do in combination with this automotive simulation models, and that is Model Desk. So if you imagine you have such a large model which models the engine, the powertrain, and so on, it's a little bit difficult, for example, to switch between different kind of motors or to configure these models to a certain thing that you need. And that's why there is a graphical user interface called Model Desk that presents this configuration data in a more user-friendly way. So, for example, here you have different diagrams, and then you have certain entry fields where you can adjust some parameters and so on. And this makes it much more easy to configure this automotive simulation models for what you want to do. Okay, and then there is this virtual testing that I will explain in a few minutes in more detail. And the most important product of the virtual testing is the product called VEOS. And it's a shortcut of Virtual ECU Offline Simulator. And basically, this allows to generate so-called virtual ECUs that represent real ECUs in a quite good way, and to simulate a set of virtual ECUs and the appropriate environment model. Okay. And to finish this overview, there's one final product that's somewhere found in the middle. And this is Synect. And Synect is basically a database that can store development and testing artifacts from all phases of development here. So, for example, you could imagine that if you have in the requirement phase, if you define, for example, certain parameters, and then you have this coding phase, and then, of course, you want to implement these parameters, and maybe you want to implement certain variants of these parameters, and so on. And somewhere here in the testing phase, you want, of course, to test all these variants, and you associate test data with these parameters, and so on. So basically, you need a connection of all this in the development phase, and that is what Synect provides. Synect is not only a database, as shown here, but also a user interface. So basically, you have this user interface where you can see these parameters and associate data to it and tests and so on. And you can, for example, configure variants for certain products and for certain product lines and so on. And all this is done by the Synect tool. So that is just a brief overview about DSpace, so you can better estimate what DSpace does and how all these products play together. And of course, as I said, Many of these products play an important role in the area of virtual validation. And so we'll come back to some of these products. Okay, so before we finish this presentation of DSpace as a company, I would like to tell a little bit more about my work at DSpace, because it could be interesting for you to better estimate what typical jobs are at DSpace. And so let me tell you something about it. So I studied computer science in Paderborn, and I am at DSpace since 2007. And I'm working in the department of application engineering. So one big area of application engineering is to build all this hardware-in-the-loop simulations according to customer requirements. That's basically the biggest part of the application engineering department. But I'm working in a quite different area. I'm working mostly in the area of target link and system desk. So target link and system desk. So you may wonder why or what this has to do with virtual validation. And the thing is, as you will see later, this system desk tool here has really a lot to do with virtual validation, because it is an AUTOSAR tool, and virtual validation is not really thinkable without AUTOSAR. So AUTOSAR is a kind of enabling technology, because it defines certain interfaces and standards that are needed to provide real effective tools to do virtual validation. So what are typical engineering tasks that I do? So first of all, I advise or support customers in using our tools. So for example, how can things be done in general? So it's not quite obvious how to solve certain problems in these tools and so on. Or another thing is, if you do, for example, automatic code generation, then there's a question, okay, we have code, but it's not efficient enough, so maybe it consumes more memory than we have on this ECU, and so the question is, how can we adapt the code generation process or the models to, for example, improve the efficiency of the code? That's a typical question in my working area. And the other thing is the development of company-specific tool chains and customer-specific additional tools and so on in all these fields. So it's, for example, it's quite common that companies have their own databases, and for example, the software architecture can be generated from these databases, and then, for example, they have to be imported into our tools, for example, into System Desk. And then you need, of course, the right automation tools that do it automatically. And that's a typical tool chain development task. And of course, sometimes there are customer-specific needs for additional tools, and then they will develop in our department too. So basically, we are working with a lot of different implementation techniques. So, for example, in the MATLAB case, we are doing M development. Much of this automation of DSpace products is done in Python, and then some things are developed in C, and high-level tools are even developed in C# and so on. So this is very different things that we are doing there as an application department. Okay. So this is all what I wanted to tell about DSpace and myself. And now the next topic would be the actual virtual validation. So maybe you've question of DSpace, about DSpace or about myself, then that would be the possibility to ask them. Okay, no questions? So now let's start with the actual method of virtual validation and of course the tools that are behind this method. Let's start from the beginning. So what is virtual validation? You also have seen an example what you can do with it. You can do this virtual test drive, and the general task is the following. So you have, or you will, at some time in the future, you will have a real ECU, and you will put it in a real car, and then you will test whether this real ECU works. And the idea is during the development phase you don't have the real ECU, but you may have, for example, the software that will eventually run on the ECU, or you have a previous version of the software. And so the goal is to have a representation of this ECU in software. And of course, to be able to test it, you also need a representation of the environment, in this case the car, in software. And the idea is to do this validation purely in software. And of course, the goal is to have a maximally realistic software representation of the ECU. And of course, it is a nice thing to have it in the earliest possible stage in the development process, because if you find the problems earlier, then you can save a lot of time. The other thing is that you, as I already said, that you want to be able to do these tests here without any special hardware, and you don't want to do just a unit test with some part software here, but you really want to do system tests in general. So you want to put all things together in a very early stage, and then you want to try whether it works without having any hardware. That is the key of virtual validation. Okay, so how can we approach this topic? So from my point of view, it is very motivating to have a look at a real customer use case. So how do customers work and what problems do they have? And this basically leads to virtual validation automatically. So I would like to go into this topic by discussing a really realistic workflow real customers have. And let's start with the workflow, with the easiest possible workflow, the classical testing approach. Okay, consider we have a car manufacturer who typically does not do the development on his own, but who has suppliers who, for example, deliver these ECUs and who are responsible for the base software of these ECUs and so on. And the typical workflow is that the car manufacturer develops software components and then passes them to the supplier, and the supplier is responsible to really integrate them on the ECU. And then this ECU would be sent back to the car manufacturer, and the car manufacturer would then test them in the real car. And that's a traditional development workflow, I think. And that works, of course, but there are some problems possibilities to improve the workflow. So, for example, of course, the testing needs a real car, and so yeah, you have to have this resource here. You have to build it in a car, and if there's no car available, then it's of course a problem. So you can't test all the things in parallel, but you have to wait when the car is available and so on. And in addition, the testing can be dangerous in some cases. So for example, you want to test a braking system and the braking system doesn't work, then you could produce a crash, and of course this is quite problematic. And another problem is that no test automation is possible in this case. So even though you have successfully tested your braking system, and then you develop a new version, then you have to do all the tests manually, and there's no way how to automate it. There are maybe ways, but it's quite difficult to do that. Okay, so and of course these problems are known since years, and there are also solutions since years. And the solution is the hardware in the loop simulation. So of course you have discussed it, but since this directly leads to virtual validation, it's a good thing to just repeat this. So basically you can replace the actual testing in the car with the hardware in the loop simulation. And in this case, you still have this electronic control unit, and instead of testing it in a real car, you will plug it to a hardware in the loop simulator, and then you can do the things. For example, you can simulate without having the risk of a car crash, and you can of course automate tests and so on. So all these problems that were mentioned on the previous slide are basically solved using this technique here. But there are other problems, and the other problems have something to do with the cooperation of the car manufacturer and the supplier. So you have to imagine that so if you give the software components to the supplier, it will take maybe a week or something until the supplier has created a new version of the ECU and passed it back to the OEM. And so there's a huge delay, and if something goes wrong, so for example, if that doesn't work, then you have to do another cycle of this week, and this takes a lot of time. And so this is a critical thing in this development process. And of course, if you want to do these tests, you still have to have hardware. So you need this physical ECU, and now you need this physical hardware in the loop simulator. And so this hardware is still a limited resource. And for example, you can't do tests in parallel if you don't have enough of these hardware items around. Okay, and the last problem is, so for example, the OEM delivers software components and the supplier integrates them, and then the ECU doesn't work. So who is responsible? No one knows, because, or other way around, it must be investigated quite difficultly. So the OEM needs a way to test the software components before actually passing them to the supplier. And that's where virtual validation comes into play. And of course, virtual validation also solves all of these problems here. Okay, so how does virtual validation work in this picture here? So basically, instead of generating a physical ECU, one generates a ECU representation in software. And the advantage is that in this case I shown here, or in the real customer use case, the automotive manufacturer can create these virtual ECUs by himself. So he is not dependent on the supplier in that case. And basically you just take your software components and create a kind of virtual-based software, and then you get a virtual ECU, and then you do a similar thing like testing hardware in the loop simulation, but you basically replace the hardware in the loop simulator by the virtual ECU offline simulator. And then you plug in this virtual ECU here, and then of course you also have to plug in your environment model here, and of course you can also plug in other electronic control units, and then you can do a simulation purely on the software level. And that is the key idea of virtual validation. Yeah, right. Okay. And now let's go a little bit deeper into how virtual ECUs really look like, what different kinds are there, and how they are created. Okay, before that, let's have a look at how the actual testing is done. As I mentioned before, in the area of the HRL testing, there are these different tools I've presented here. So, for example, Motion Desk, where you have this 3D visualization, and Control Desk, where you have this virtual cockpit, and for example, this automotive simulation models, who provides the actual simulation mechanisms of the environment, like the car and so on. You have Model Desk to configure all this, and you have, of course, other tools, for example, to do the test automation. And all these tools are actually invented by for the HIL hardware in the loop simulation use case. The key idea is to reuse all these tools also in the area of virtual validation. So you can basically just replace the HIL by the virtual ECU offline simulator, and you can basically use all these tools to do simulation of on this level here too. And so you can reuse all the configurations that you have done here if you have already done HRL tests. Now that's a very important thing, that you don't have to invent the wheel, but you can reuse it. Okay, so next topic would be to understand a little bit more about how virtual ECUs are created, and what different kinds of virtual ECUs and so on are required to do a simulation. And first of all, we have to distinguish between two different things that you can see here. So all the things that can be plugged into VEOS are called virtual processing units. And basically, there are two different roles of these virtual processing units. So you have environment VPUs, for example, this here, which are responsible to simulate the actual environment. So in this case, the car, the motor, and so on. And then you have the real virtual ECUs, which represent counterparts of real ECUs with all its features, for example, calibration services and base software and so on. Okay, and as an example, in this case, we have two virtual ECUs, and we have one environment VPU. Well, that's the one important difference. And as I said, the general term of all this is VPU or virtual processing unit. Okay, and then there can be different sources where these VPUs come from. So, these sources are supported by the DSpace tool, so by the VEOS tool. So maybe the source that can be understood easiest is the Simulink model. So if you imagine you have a Simulink model, model with ports at the highest level, then you can just convert it to a virtual ECU, and that's fine. Okay, but you have different other possibilities to create these virtual ECUs. So for example, you can even use handwritten C code, and then of course you need some kind of tool where you say, okay, these are the functions that are my step functions, and these are the input variables, and these are the output variables, and so on. And there's also a solution of DSpace where you can use handwritten code to generate a virtual processing unit. Then there's an ASAM standard, and this ASAM standard defines so-called functional mockups. And basically, it's an XML description. You have a piece of C code, and you have certain functions, and it describes what functions have to be called and which interfaces are available, so which signals. And then you can use such a functional mockup to generate a virtual processing unit. And last but not least, you can also use AUTOSAR ECU descriptions to generate a virtual processing unit. I think you know the basics of AUTOSAR, so you know there are software components, and then there is a runtime environment which connects these software components, and then there's base software to communicate with the outside or to provide certain services of the ECU and so on. And if you have this description, you can also convert it to a virtual processing unit and then plug it to VEOS. And the thing is that this description here is a much more detailed description than the information that is provided here, because here you have base software and scheduling things and so on, task priorities. And so there's a quite different abstraction level of all these VPUs. So basically, you could use all these sources here to produce environment VPUs, and you can produce virtual ECUs. But typically, you would use the Simulink source here to use the environment model, and depending on the level what you want to test, you can use a simple source. For example, you can use a target model to create a virtual ECU. Or if you really want to test your software components deeply, inclusive the effects of base software and so on, then you would use the Autosar ECU description as a source of the virtual ECU. Okay, so most of these creation processes here are quite easy. So the most complex one and the most important one, if you really want to have realistic ECUs, is an Autosar ECU description, and that's why I would like to go a little bit more into the details how such a description looks like, or what it has to consider. So for that purpose, we have to look into how Autosar works, and I think you have seen this picture before, right? So you know the Autosar methodology defines an item like software component, and basically these software components are first quite individual, and then they are combined to an architecture. And this architecture defines the communication between these software components and so on. And at some place in time, these software components are placed on a specific ECU. And after that, you can generate a runtime environment where the communication of these software components are implemented on this ECU. And you can configure base software which is needed to make a complete ECU, in the sense that the ECU can do, for example, bus communication to communicate with other ECUs, or it can read the input data from sensors, for example, to measure certain things and so on, to access NVRAM and to do all these things. So basically, you can understand the role of the abstraction level of virtual processing units by having a look at this picture here. So basically, this is an example of an Autosar ECU, so where you have software components, the runtime environment, and the base software, and all this can be packed into a virtual processing unit. But on the other side, you can also have a virtual processing unit that only has these functions and which directly communicates to the outside without having any base software, without having any special services, and so on. So these are the different abstraction levels. Okay, and here at this picture, we see that if you have a look at software components, the communication between software components can be quite different. So first of all, if the software component is located at the same ECU or virtual ECU, they can pretty much communicate directly using the runtime environment. This is this line. So if they are located on different ECUs, for example, there would be a software component here, they typically communicate over a bus. And so technically, the communication goes through the communication stack. So that is this kind of base software modules here, and then going over the bus to the next ECU, and then going up this way, and then you have this communication over the bus. And the last level of communication you can see here. So there is an abstraction called Virtual Processing Unit Port. And this VPU port, in some respect, corresponds to a kind of I/O port of a real ECU. So for example, you have a sensor, and then you have a wire connection from the sensor to the ECU. And in some respect, this VPU port corresponds to this plug-in where you can plug in the sensor. And you can also configure virtual ECUs to have these VPU ports, and you can connect ECUs by these VPU connections. And these are basically the three different ways how things can communicate on this level here. So the summary of all this is we have three levels of communication via RTE, via VPU ports, so in this case, for example, and via bus, so going this way and then up here again. And we have different abstraction levels, whether we use a pure functionality model without having any base software and so on, or we can have a much more complex ECU model where we have, for example, base software services like accessing NVRAM or having an ECU state manager, for example. And we can decide whether we want to have bus communication to communicate between different software components of different ECUs. So this leads to different levels of detail that can be used to do a virtual simulation. So, and I have prepared three different typical levels how the virtual offline simulation is actually used. So if you start, maybe if you only have a Simulink model so far, then you could already do virtual validation by creating a VECU on Simulink level, and that would look like so. And then you can connect the Simulink ECU with an environment VPU, and then you can use the Veo simulator to simulate the system. And in this case, you don't have AutoSar at all, and you only do a pure function simulation. That's totally okay, but of course, in this case, this ECU is not very realistic, and you are also restricted in the things that you can do. So for example, this is quite impossible if you really have software components, because typically software components have interfaces to base software functions. For example, to store data and read data from NVRAM and so on. And you basically have to implement stub functions or something like that. So this is really only useful for control algorithm without all this additional stuff where you need the base software. Okay, then we have a second phase where you may have implemented all these software components, but where you don't want to worry much about the actual ECUs. For example, you have not decided what software component should be placed on what ECU. You have not developed your bus communication matrix and so on. So you only want to simulate a set of software components, so your software architecture, on a quite detailed level. And as I said, as all these software components use base software functions, you need a kind of base software module, but it doesn't have to be exactly like the one you have in your final system. And this is the stage where you would typically do an VFB level simulation. So you simulate the AutoSAR architecture, but you don't consider bus communication, but you use the virtual function bus level for the communication of the software components. So you would put all the software components of your architecture in one virtual ECU, and you would use the base software services, but you would not use the base software services in a similar way as they would occur later, but you would generate an implementation that just works in this case. And you would not use a bus communication, but everything, internal communication here, is done on the RTE level, so on the virtual function bus level. Okay, and then finally you have the most complex way to use a virtual validation approach. You can model a multi-bus or multi-ECU system that also has a bus communication. And so you would basically model the virtual ECUs in the most realistic way, using a quite good approximation of the base software that will be used later, and then you will configure how the different signals that are produced by the software components are mapped to bus signals, and then this communication is really sent over a simulated bus and will go to another other ECU. And so the ECU partitioning is really like it will be in reality. You will use the base software services like in reality, and you will have the bus communication like in reality. And as I said, these are the typical abstraction levels, and basically it's up to you which level you choose. Of course, this is the most realistic one, but it is at the same time the most expensive one, in the sense that you have to configure all the things here, of course. Okay, so as you can see here, whenever the detail level is quite deep, you have AutoSAR involved. So AutoSAR is a kind of enabling technology, because if, for example, these interfaces here are not defined, you basically don't have a chance to provide a generic tool that supports this creation of the virtual ECU. And to think about how these virtual ECUs on this level are created, we have to think about what has to be done to configure all the things here. Okay, so this slide shows the generation process of virtual ECUs on on the most detailed level. So basically, you can have a virtual ECU here that quite realistically represents an actual ECU. And the key tool here is first the system desk tool. So the tool that is basically used to define the software architecture. And as I said, you can generate the runtime environment, and you can configure base software properties and so on. Well, this is a quite important tool to do this use case here. And of course, we have also VEOS involved because VEOS is a tool that actually creates a virtual ECU. And now let's go through all the steps that are required to get an VECU on this abstraction level. So first of all, we need, of course, the software components that you want to integrate. And these software components can be, for example, developed by TargetLink. So TargetLink can just generate software components from Simulink models. And of course, I think MathWorks has a similar feature to generate software components. And these software components, first of all, have to be imported into the system desk tool. And then you have to configure certain things. And basically, if you know a little bit about AUTOSAR, you know that it is quite complex to configure all the things. So let's see what has to be done in detail. So first of all, you need, of course, your software architecture. The software architecture, you can see it here a little bit, is basically the connection of the different software components. In general, you can import the software architecture, or you can create it in System Desk. Okay, so that's the architecture level. So the next thing is you have to somehow configure the base software. So the base is a little bit problematic because configuration of the base software, of real productive base software, is not done in a day or two, but it's you need weeks to do that because it's really complicated. There are so much of properties and so on. And basically, you would have to do that here in System Desk too. Basically, you can import configurations, or you can do them here in System Desk manually. And the thing is, because it is so complex, there are certain automatic configuration mechanisms available here in System Desk, and that makes it quite easy to do the base software configuration in respect to a real production code base software system. And in addition, you have to have in mind that the base software that is configured here is only a simulated base software, meaning that, for example, you don't access maybe a real bus, but only a simulated bus. You don't access real NV data, but you access simulated NV data. And so you don't have to have so much properties to configure it. And so that makes the things a little bit easier too. But in principle, you have to worry about it, and you have to configure it to have a real, realistic ECU representation. Okay, the next thing is we need, if we decide to do it, we need a mapping which signal of your software components here represent or is represented by which bus message. Basically, you normally import the communication matrix of the bus, and then you associate all the signals here to certain bus signals. And then the generator is able to generate certain base module configurations that reflect this, and that makes it possible to send this data over the bus. Okay, so if you have done all this, SystemDesk is able to generate a so-called virtual ECU implementation container. And this implementation container represents basically this ECU that you have described here in a platform-independent way. So basically, on this level here, you have a real implementation of software components. So you have C files, and you have a description of all this. So all this here only contains of descriptions, but there's no C code involved. So on this level, there's a little bit C code added, and that's the C code that implements the RTE, the runtime environment. So basically, the communication on this level is already fixed, implemented in C code, and there are also other small other types here of the base software that can also be generated. But in general, this part here contains only a description of the base software because, as I said, it's platform independent. So yeah, basically on this level, it's you have not decided whether you want to simulate it or you want to put it into another system where you can really do for example, real bus communication. Okay, so basically this VECU implementation container is only an intermediate representation of the virtual ECU. The real virtual ECU is created by VEOS, and this virtual ECU then represents real binary that can plug into the VEOS system and simulate it with other virtual processing units. And the difference is that on this level here, the base software implementation is generated. So VEOS takes these descriptions here and really generates a base software representation, implementation. And then all the things here is compiled into a real binary that can run on a PC. And the result is then called virtual ECU. Okay. Yeah. As you see, it's a quite complex process, but depending on the requirements, you can, of course, automate things. So I will later explain or present some use cases of real customers, and partially they have tool automations where you can just put in this software components into an automated process, and you don't have to do anything here at all, and then finally you have this virtual ECU generated automatically. Of course, this is only possible if you have some knowledge about what has to be done in general here. Okay, but we will come to that later. So I have explained a lot of details here about what VEOS can do and how it is done. And so maybe it's time to do a little summary what the real essence of VEOS is. So basically, VEOS provides the possibility to generate virtual processing units from different sources. I mentioned, for example, Simulink and AUTOSAR. So these are some of the most important ones. Of course, there are others. And as I've explained, in the course of AUTOSAR, it is really a hard work in the sense that you have to translate base software descriptions into real base software implementations. So this is not a so easy task to do that. Okay, the next thing is Yeah, that's what I meant. So basically, WEOS is able to implement also the base software services for these things, so for the operation system, for the NVRAM manager, for the COM stack, calibration services, and so on. Okay, then there is the area where the connections of virtual ECUs are managed. So for example, WEOS provides a mechanism how these connections are created. You can basically do drag and drop to connect one VPU port with another VPU port. And you can, of course, WEOS is of course able to implement these connections in the sense if you run an actual simulation, then the data sent to the one VPU port will of course arrive at the other end of the receiving VPU port. Okay, then of course there's a management of the VPU execution as such. So you need basically a virtual simulation time like you have in Simulink, and you have to call the different functionalities of the different virtual processing units at the right point in time and so on. Of course this is managed by WEOS. And last not least, you have a simulation of some hardware items. So most of the hardware items are not quite difficult to simulate. For example, you need a representation of non-virtual RAM, but that's not a big problem. But a more advanced topic is the simulation of the bus communication. But as you know, in the automotive area, there is the CAN bus. It's one bus that is commonly used. And of course, you cannot send an infinite amount of data over this CAN bus. So basically, you can, if two ECUs want to send data, there's a kind of priority defined in the CAN bus, and only one ECU can send this data. And so maybe some data is sent later and so on. And this can be simulated in this virtual simulation too. And then you can, for example, analyze this simulation here and see whether the bus communication works or whether you have a too high bus load and maybe you have to do something to fix that. And you can simulate that too. So all these are features of WEOS, and in this way WEOS enables you to do quite realistic simulations. But there's one thing that is not actually part of WEOS, but it is from the user perspective quite important part, and that is that you can use all these nice front-end tools that you already know from the Hill area. So you can, of course, control WEOS by controllers, for example, to tune the parameters during simulations and to read the data and plot curves and so on. You can use MotionDesk to visualize the behavior, and you can use ModelDesk to create the environment simulation and so on. So basically, WEOS would be more or less useless if you would not have these powerful tools here to really do something interesting with the simulation. Okay, yes, I think that's a good thing for a good time for a break. I only have one additional slide to finish this this part. What we have seen is what WEOS does, but one can go one step further, and you can, if you have this process, you can reuse it with a little bit different focus, and that's what I add now to finish this topic. And the thing is, I've explained that systemd can generate this target-independent representation of a virtual ECU. Okay, and I have explained how VEOS can generate a real virtual ECU from it, and then you can do virtual validation, you can do offline simulation. And the thing is, so if you have this quite realistic implementation and platform independent representation, then you can again combine it with real-time hardware. So for example, we have this prototyping platform, and it would be nice, so if you have this, you can load it to the prototyping platform, and then you have, for example, a system that can do real bus communication in real time, so basically representing this is a kind of physical representation of the ECU, which can be basically used like a real ECU. So you can use you can load it to prototyping hardware. That's one use case you nearly get for free having this technique. Another use case is you can also create a kind of ECU representation for the Scalexio system, so for the hardware in the loop simulation. So, and this is quite interesting use case too. So for example, you know that if you do hardware in the loop simulation, one possibility would be to just plug in one ECU and let the hardware in the loop simulator do the remaining simulate the remaining environment, including, of course, some other ECUs. Because, for example, if you have a car, then a car representation, then you need a kind of motor control unit so that the car will work and so on. And basically, you can increase the level of detail by plugging in a real motor control unit, for example. If you don't have a real motor control unit controller, then you can plug in a virtual one. So you can, for example, use this to add ECUs to a hill simulation system where you don't have physical ECUs, and so you take virtual ECUs. But nevertheless, you plug it to a system that does real-time simulation of at least one physical ECU. Okay, and that is, as I said, that is not virtual validation anymore, but that are additional use cases that are possible if you once have this base techniques. Okay, so maybe the last slide here is a little bit confusing. I don't know whether you understood exactly what I want to tell you. But I think in general this is a rough overview what virtual validation does and what techniques are used to enable it. And I think it's time for a break, but before that, you can ask questions if you like. And maybe we can, if you don't have questions now, I can also ask questions after the break if you like. But if you have questions already, then feel free to ask them now. Okay, you have a question.
The tools for the ECU simulation, is it independent of the hardware architecture of the ECU? Or maybe it's not important on this stage?
Okay, the question is whether the tools of the ECU simulation are independent of the hardware architecture. And I think the answer is yes. in principle, they are quite independent. So the hardware dependence comes from, or basically the hardware dependence is introduced at the base software level. And as I said, the base software is basically, so that is the most important use case. The base software is normally not the actual base software that would be used later on, but it is base software that is partly automatically configured by system disk, and the implementation of the base software is generated by the VEO system. And this implementation is, as I said, not a real implementation, but an implementation related to the simulated environment. And so, yeah, as I said, it is not directly related to the hardware. Again, what? Right. That is an important. The question was whether the supplier of the ECU is involved in this process, and the answer is it's a very important use case that the OEM, for example, can do this whole process without involving the supplier. Okay, there's a little additional thing. So there are customers who would like also to validate their base software implementation that is really used at the ECU later on. And so there is a severe effort to make that possible, to use at least some levels of the actual base software, to integrate it into the simulation, to even validate this part of the base software. Well, that is partially possible too, but of course, at some point you have to do a cut and you have to simulate the rest, or to implement the rest in a different way. Okay, are there more questions? Okay, then I think it's time for a break.